general set of solution. Remember, the Wronskian is the functions and then their derivatives are in the matrix of 2 by 2, and take the determinant and it has to be non-zero. Then we're gonna move on to this characteristic. Who remembers what characteristic equation is? You remember? Raise your hand if you remember. So like if you had y double prime plus some a y prime plus b equals 0, then we said y is equal to e to the power of rt, remember? That was our yes. So to plug it back in, you're gonna get r squared plus ar plus b equals 0. So that's called a characteristic equation. So when I say characteristic equation, that's the one. You don't need to write this, it's already like been written many times. I'm just kind of reminding you. Now we want to look at characteristic equations when they have repeated roots. So that's so let's talk about power series before we go to the complex roots. The power series and Euler's formula. So the first thing that I want to remind you was the Maclaurin series, and then it was a special case when x was 0. I think it was when x is 0, was it called the Maclaurin? Was it when x was 0 was Taylor?
Taylor.
Well, when x was 0 was
Taylor.
when the initial condition was 0.
That's McLaren. So like all McLaren series are Taylor series, but not all Taylor series.
Right.
McLaren.
So essentially, if you have a function f of x, you can approximate the function with linearly combining all polynomials of all degrees, essentially. So you can write any function as a linear combination of a bunch of polynomials, okay? And that approximation is only done at one point. So like at one point you approximate that and gonna expand it. So that's why we call it like at x0. But when you're talking about Taylor series, that point is literally just the 0 point, and makes life so much easier for these approximations. And these are the things it was in your Calc 2, like in the power series section when you were studying. But essentially, an f of x can be approximated as f of x0 plus f prime at x0 times x minus x0 plus f double prime at x0 over 2 factorial times x minus x0 squared, and then keep going. So you go first derivative, second derivative, third derivative, and when you're a third derivative, you're like over like 3 factorial times x minus x0 to the power of 3, and then the fourth factorial or the fourth derivative. So there should be some conditions about the function, and I think it's called analytic, which means the function has like nth time derivative on a disk on like certain area, like such that you actually can take the derivative of it. If you cannot, then there's nothing to talk about. So there's like some background work needs to be done in order for the function to have a Taylor series. It has to be differentiable, it has to be continuous, it has to have certain conditions in a certain domain so that you can actually take its derivative. If it didn't have it, you weren't able to take its derivative. So just imagine you have like a domain that this function is nice for you. Let's just put it this way. It's working for you. So, but then for Taylor series, you could just say f of x is equal f at 0 plus f prime at 0 times x plus f prime at 0 times x squared over 2 factorial plus f double prime, f triple prime at x at 0 x cubed over 3 factorial and so forth. So it makes it a lot easier to do. So it looks like it's some sort of a, like you can write it in the summation form. So it would be written as the sum of f of n factorial at the point 0 times x to the power of n over n factorial, essentially, and going from 0 to infinity. Alright, so as an example, you could look at, for like a e to the power of x, let's say. So let's call it e to the power of x. So what is e to the power of x at the point 0?
1.
So it's e to the power of 0, which is 1, plus, what is the derivative of e to the power of x? Is itself. So every derivative essentially is itself, you know. So that means every derivative of itself at the point 0 is still gonna be 1. So f prime, which is e to the power of 0 again, times x. So the next point is x over n 1 factorial over 1 factorial, you can write it, plus the second term is again e to the power of 0 again, times x squared over 2 factorial. The third one would be again e to the power of 0 times x cubed over 3 factorial, and so forth. So essentially you can write this as x to the power of k over k factorial, k going from 0 to infinity. That's e to the power of x. Who has never seen this before? Raise your hand. It's okay, I mean, it's not on you.
I didn't actually learn the first part very much. It was like just kind of, here's the series, and then like we manipulated it, like, oh, here's the series for e to the x, find like 3 e to the x squared or something.
Has anyone seen the proof for Taylor series? Like, why can you write a function as a bunch of like addition of polynomials?
I don't recall.
Here's a good extra credit problem for you. Dig up the proof for Taylor series. Like, why is this true? Okay, before I move on to the next example, remember imaginary numbers? So you have I, to the power 1 is I. What is I squared equals?
-1.
-1. What is I to the power of 3 equals?
-I.
Yeah, because it's -1 times I, which is -I. And then what is I to the power of 4 equals? 1, because -I. So essentially I to the power of 3 is -I times another I is -1, so it's just 1. So it's like mod 4, essentially. Every 4 you kind of recycle and bring back. So I to the power of 5, essentially you just take a mod 4, and whatever remainder is one of those. So it's just I to the power of 6 again is like the I squared, so it's -1, and so forth. So this is important to know. So why don't you guys take a second, I know some of you have already done this, but why don't you take a second to look at e to the power of ix in terms of Taylor series. So you have to follow this f of 0, f prime at 0, f double prime is, and keep so forth, go forward, and try to derive up the Taylor series. It's very similar to e to the power of ix, you just have that extra I, so it can help you with just following this. So when you think about it, really the only thing changed is the I added beside the x. So you could just take this x and replace it with ix. This x again with ix, so it would be ix the whole thing squared, ix cubed, and then you can follow with what I just said. So it would be 1 plus ix over 1 factorial plus ix squared over 2 factorial plus ix cubed over 3 factorial, and keep going. Now we saw that, like for example, ix squared is negative, like I squared is -1, so it's going to be negative x squared, so it's going to be 1 plus ix minus x squared over 2 factorial. The 3 would be like, this is equal to negative I, so it would be negative I x cubed over 3 factorial. If I'm going too fast or you're not following, just tell me what's going on.
Aren't you supposed to take the derivative of e to the ix? Like,
Yes, so I already did that here, like kind of quickly, because I'm following this pattern.
okay.
I've already did the e to the power of x, the derivative of e to the power of x itself, right?
Right. Is it the same for
So
e
you
to the
just
ix?
substitute instead of x, you put in ix.
So the derivative of e to the ix is e to the ix?
Because I is like a coefficient, right?
Right.
So, and then so the I will come down like that many times, so it will become the same thing. Because like, if you take the first derivative of e to the power of ix, then an I will come down.
Yeah.
And it would be then e to the power of ix, but at the point 0.
Which
So it would be just like, just
I.
1.
Oh.
The second derivative would be like you're doing this twice.
Right.
So you just have an I square. And then, because this is at point 0, right?
Mm-hmm.
So it'll just be I square. So that's where this I square comes and I cube comes. And then the third derivative of e to the power of ix at the point 0 is you have 3 i's coming out 3 times. But then e to the power of ix is like e to the power of 0 again, so you just get I cubed.
Okay, gotcha.
So keep writing this, then you get the fourth one, which is just 1, because I to the power of 4 is 1. So it's plus x to the power of 4 over 4 factorial. Then the fifth one would be just I, so it's plus I x to the power of 5 over 5 factorial. The sixth one is like 6 mod 4 is 2, so it's just I squared, so it's just negative 1. So it's negative x to the power of 6 over 6 factorial. Seventh one would be 7 mod 4 is 3, so it's negative I, so it's going to be negative I x to the power of 7 over 7 factorial. And then 8 would be just going back to 1 again, because 8 mod 4 is just 0, so you get x to the power of 8 over 8 factorial, and keep going. If you notice, you kind of have an alternative, like one has I and one doesn't have I, like has it, doesn't have it, has it, doesn't have it, has it. You notice this is like every other one has an I component. So what we could do is we could take the real component and the imaginary component, so we can factor out a whole I. So this will become the following. It will become, the real part would be 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial minus x to the power of 6 over 6 factorial plus x to the power of 8 over 8 factorial. Keep going. And then plus I factor, you have x minus x cubed over 3 factorial plus x to the power of 5 over 5 factorial minus x to the power of 7 over 7 factorial. Keep going. All right. Now what's interesting is that if you, who remembers seeing these before in your Calc 2 class?
Sine and cosine Taylor series.
Who remembers now? Raise your hand if you remember or seen it.
I did it, I figured it out.
Okay. So
I keep my door
why don't you
online.
guys do this? Why don't you just look at the first few terms of the scalar, so let's just box this up for now. This is just for now. That's e to the power of ix, okay? That's the Taylor expansion of e to the power of ix. Now, why don't you guys look at this thing now? Look at the Taylor expansion for sine of x. Just the first few terms. And then the Taylor expansion for cosine of x. Just a few terms. Just try it out. So all you have to do is put in 0, and then, so sine at 0 is what?
0.
Is 0. So the first term for sine is gone. Sine at, when you take the derivative of sine, what do you get?
Cosine.
Cosine. What is the cosine at 0?
1.
1. So the second term is 1 times x. Again, what is the derivative of cosine now? Negative sine. So the third term is negative sine at 0. Boom, gone, 0. So you just have to keep taking a derivative, plug in 0, and then keep track of your polynomial. I'm going to do this a little quickly because I don't want to spend too much time on this. However, try the first few so that when I talk about it, you grasp what I'm saying. One more time. Okay. So I'm gonna talk about this rather than writing everything down. So the first term is sine at x equals 0. Sine of 0 is 0. So the first term is 0. The second term is you take the derivative of sine, which is cosine, right? You plug in the 0. Cosine of 0 is 1 times x over 1. So that's just plus x. The third term is the derivative of cosine, which is negative sine, but you plug in 0, boom. So every other term is 0. So that's 0 again. Plus, or let's see. Fourth term, it's the derivative of negative sine, which is negative cosine. Negative cosine at 0 is negative 1. So you get that in negative 1 here. Then, what is the term that has the x to the power of 3 over 3 factorial? X to the power of 3 over 3 factorial. Then you take its derivative of that, it has a sign again, so it's 0 again, and then take its derivative again, it has a minus behind it, so it becomes positive, and it's positive x to the power of 5 over 5 factorial. So you can see this kind of like, you have alternating sign with only odd powers. X cubed, x5, x7. So the next one would be negative x7 over 7 factorial, and so forth. But do you see that up here? It's this term. It's like the second one here. If you take the cosine, let's talk about the Taylor expansion for cosine. What is cosine at 0? 1. And it's just that, that's it. The second, the derivative of cosine is sine. You plug in 0, it's gone. So the second term is 0. But then the derivative of cosine would be negative sine, and then the derivative of negative sine is negative cosine. So negative cosine at 0 is negative 1 now, times x squared over 2. So it's negative x squared over 2. Then you can see the same pattern. The next one would be 0 again, because when you take a derivative of cosine, it's sine again. And so the pattern would be similar to upstairs, but just with even powers. So you have 1, negative x squared, x to the power of 4 or 4 factorial. Then it would be negative x6 over 6 factorial. So all the even powers. So you can see that this portion here is the cosine of x. And you can see that this portion of it is sine of x. And that's what Euler's formula is. The Euler's formula is the following. You say that e to the power of ix or it is cosine of x plus I sine of x. And that's the Euler's formula. And we're going to use that today in order to solve our differential equations. Any question on this topic? This is a background information from your Calc 2 class that you've probably seen or experienced, but it's so beautiful, I just didn't want to just like give it to you and like be like blindly accept it, you know. It's nice to see it. Again, for extra credit, it would be nice for you guys to do the proof for Taylor expansion or Taylor series. It might have some advanced topic in there, and that's okay, just learn those and then try it. So it's really good to do math. Makes you smarter. Like seriously, it's a brain push-up. Like that's like the one like feel that it's the brain push-up. Like you push up your muscle, you do push-ups to get stronger on your body, the brain just gets smart. Playing chess is another one. Strategies.
I never got a runner's high from doing like learning until I hit physics. And it was like word problems and math. Combining. There was a problem, I forget what it was even about. But it took me like an hour and a half. And after I figured it out, I felt like I just ran like a marathon.
Oh yeah. Oh, 100%.
Like just all those endorphins and like, oh yeah, felt pretty good.
On the other hand, is a pretty I guess some math skills are good for survival, but like it's not necessarily what you need to survive. I think human instincts are the most powerful thing that we're trying to suppress so much right now as a society, but like once you get to a point where you actually need to survive and you know, as a human being with the rest of the animals on this planet, then you don't really need math much. You know? So maybe soon we'll get there. You know, who knows where this war is going. I think Putin is really itching for some all blown out war, and it's just like, you know, when you want to start a fight, you just like, hey, what's up? What do you want? It's like doing that, you know.
There are some theories that a bunch of the old world leaders are getting, you know, getting feisty because they're getting old. They're like, all right, let's get this over with.
Yeah. So we're gonna talk about complex roots of the characteristic equation.
Let's leave that behind the scenes.
So, as I kind of stated a little earlier, we're dealing with this differential equations a y double prime plus b y prime plus cy equals 0. And in order to solve this, this was, remember A, B, C are constant coefficients, they're not any functions of t right now, we're not there, you know? So A and B and C are real numbers. A, B, C are real numbers. And let y to be some sort of an e to the power of rt. Okay? Then you get the following characteristic equation, which is ar squared plus br plus c equals 0. Okay? Now, remember the quadratic formula? R is equal what? Negative b plus minus b squared negative 4ac over 2a, right?
Yes.
What happens if b squared negative 4ac is negative?
You got imaginary numbers.
You get mad. So if b squared negative 4ac is less than 0, then the roots, this r is gonna be some lambda plus minus I nu. I'm just using these letters because the book is using it. You could use anything you want, it's not a big deal. But what is lambda? Lambda is negative b over 2a. And then what is nu? Nu is like the
real part, I guess.
yeah, like take the I out. So the new I, let's put this, the new I is the b squared negative 4ac over 2a. That's essentially that part. But you'll see that, you know, when you're solving it actual with numbers, it comes out, you know. So then, so you have this lambda plus minus IU. So what is your solution then? Then your solution is your y1 of t is e to the power of lambda plus I nu, the whole thing times t. And then your y2 of t is e to the power of lambda minus I nu of t. Just like this. Well, that doesn't really help because how do you graph this? How do you work with it? You know, if you're solving for some realistic model that you actually need like a solution to show, and you can't really talk about complex, you know, coordinate system and whatnot. So then, but there is a way to fix this, and that's by linearly combining them together and getting rid of some of the imaginary parts. But what we actually need, the Euler's formula. So now here we need to, so remember the Euler's formula, which was e to the power of it is cosine of t plus I sine of t. Now by substitution, I can also look at e to the power of negative it. Remember, cosine is an even function, so the negative wouldn't do anything to it, so it still would be cosine of t minus I sine of t. The other thing is good to know about this, if you substitute e to the power of I mu t, mu is just a coefficient, so that plugs into the function, so it would be the cosine of mu t plus I sine of mu t. So take these as like some sort of a cheat sheet here to work with these two. So then, let's look at the y1 and y2 now. So y1 would be y1 of t would be, can you look up for a second so I don't have to write this twice? So, are you okay if I just write e to the power of lambda t times the whole complex portion? Like, you know, because it's an addition and an exponent, I can write it as multiplication. So this would be equal, never mind, let me write it. So this is lambda t times e to the power of I mu t. That's what I was talking about. You do that. So y1 would be e to the power of lambda t times e to the power of I nu t, which would become cosine of nu t plus I sine of nu t. And then y2 of t, which is this guy, you would still have e to the power of lambda t times the cosine of nu t, but here's a negative I, right? So it would be negative I sine of nu t. So this is my y1 and y2. Okay, just listen to me for a second here. I want to do something that might buff some of you who think too rationally. All right. What do I have here? I have two separate functions that are potentially linearly independent, right? Potentially. I think they are, but I still have the I here. What does your general solution look like here? So the general solution is some c1 y1 plus c2 y2, right? So it's a linear combination of the two functions. So I can work with these two functions and linearly manipulate them to get rid of the I and still come up with two separate functions and then take the linear combination of that. We did that in a linear algebra class where you had the what are they called? The row operations. Like you could add a multiple of this to the other one and replace it with it, and it'd still be the same system. It would still have the same outcome because it was okay to linearly combine the rows and still get the same type of system. Essentially, it's the same thing I'm doing here. I want to get rid of the i's, and you can see that I can easily do that, but I just adding the two right now, I'll just get rid of the I here, and then I can subtract them and get one with the I, but I could just take I as a coefficient if it's just standing alone. And then say those are my two new set of solutions that I can see if the Wronskian is non-zero. So the whole idea of what I'm doing next, it falls into the same category of row operations that doesn't change the system. Think about it, okay? So I can add y1 and y2 here. I can add y1 and y2, and what do I get? You see those two cancel out? So I get 2 e to the power of lambda t cosine of nu t. The next thing I want to do is subtract them, y1 minus y2. This minus that. If I subtract this, if I say the first one minus the second, what cancels?
Cosines.
The cosine cancels, right? And I will have, how many i's? I would have 2i sine of mu t, right? So I would have 2i e to the power of lambda t sine of mu t. Okay, this is what I was talking about. Take this and take that as your two new solution. These, what are these two? The 2 and the 2i are just coefficients. So drop them out. You don't, it's gonna come back into the c when you calculate the c. So you can just get rid of it, drop it out. So then take this as your your new solution, u of t and v of t as your two new solution. So these are called the real valued solutions, where u of t is e to the power of lambda t cosine of mu t, and then v of t is e to the power of lambda t sine of mu t. So if the Wronskian of these two is non-zero, then we're good. So what is the Wronskian of u and v? Why do we do the Wronskian again, remember?
Check for linear independence.
Check, make sure they're not the same functions, they're not lined up in the same direction. So first is you put the functions, so e to the power of lambda t cosine of mu t, and e to the power of lambda t sine of mu t. What is the derivative of this one? I think I need more
Lambda.
space, hold on. So the derivative of this is lambda e lambda t times cosine of mu t. The derivative of this is negative nu e lambda t sine of mu t. The derivative of this is lambda e to the power of lambda t sine of mu t. The derivative of this is plus mu e to the power of lambda t cosine of mu t. Let me zoom in it for a second so you guys can copy. That's cosine.
I believe the term you mean is transcribe.
Alright. So then let's take this determinant, which is equal, okay, this times that is mu e to the power of 2 lambda t sine cosine, sine of mu t, cosine of mu t. And then I have mu e to the power of 2 lambda t cosine square of mu t. Then I have minus, I'll write it down, minus e to the power of So it's gonna be lambda e to the power of 2 lambda t cosine sine, or sine nu t cosine of nu t. And then I have minus again, did I make a mistake here?
I
Should be-
think that
Should be a minus here, right? Because,
the derivative of the first one should be plus psi t plus
the derivative of this is that times that.
psi cosine.
So the derivative of cosine is sine with a negative, right?
I think
Psi
it's,
cosine but positive.
Here's positive?
Yeah.
No, this
that's
should be
good.
negative.
I think it's just, you subtract, and then in brackets is those two.
So this times that, oh, this times this is first, so it's
Yeah.
cosine sine plus, and then minus, okay, now it's good.
Yeah, and then minus.
So minus this is good, so this will become plus, because minus minus, nu e to the power of 2 lambda t, so everything's good, there was no mistake, I just had it. So then sine square of nu t. These two cancel out, obviously, they're on top of each other, they're the same thing with the negative sign and positive sign. And then the other two becomes equal, you have the nu e to the power of 2 lambda t, but then I have sine square plus cos square, which is equal 1. So that's it, that's your result. That's your Wronskian. And it's non-zero, because if it was 0, that means nu should have been 0, but if nu was really 0, we weren't here doing complex shit. So- because nu is non-zero, so that means your general solution is C1 e to the power of lambda t cosine of nu t plus C2 e to the power of lambda t sine of nu t. Any question? So, you write the characteristic equation, you find the complex solutions, the real part goes to the e, the imaginary part goes to sine and cosine. That's it. Let's see an example. I mean, I'll have you start it. Solve y double prime plus y prime plus y equals 0. And it's a good time to take a quick break if you want to go use the restroom or something, or get some fresh air. So you write the characteristic equation for that, solve it, find the real and complex components, and plug into what we just found.